Okay, so we're moving our way through chapter 3, and today you can see the topic is inverse functions and relations. What comes to mind when you see the word inverse? Well, the opposite of 5 is negative 5. Well, what's the inverse of 5? 1 over 5, right? So it's not really opposite. We could use the word, starts with an R, reciprocal, okay? So what I like to do is think of this in terms of flipping the number over. You know, this was 5 over 1, and we flipped it over. The reason why I'm using the word flip is because we're going to do a lot of that when we come up with inverse functions and relations, okay? So let me show you what I mean. We'll start really easy. These letters A and B are both relations. The definition of a relation is a set of ordered pairs. So the way I get the inverse, and I'm going to go ahead and throw a notation at you. Let's just say, for example, this set was called f of x. Just for sake of introducing you to a notation, you may have already seen it. The way I come up with the inverse, which is denoted as f negative 1 of x. So when you see this in a context talking about functions, it literally reads as the inverse of. And getting the inverse of a set of ordered pairs is about as easy as it gets. So remember that word flip? We're literally going to flip or switch places with the x and y coordinates. So the function, the original function had the point negative 9, 10. To get the inverse, I just make 10, negative 9. I literally switch places or flip the x, y coordinates. So keep that in mind when we start talking in just a little bit about how to come up with the inverse graph. If we know ordered pairs on the original, to come up with the inverse, we just take those ordered pairs and we switch places with them, and that will give us the inverse. Okay? So pretty obvious. I'll save a little bit of time. We don't need to do letter B. So if all you're doing is looking at a set of ordered pairs called a relation, you can get the inverse of that set of ordered pairs by switching places with the x, y coordinates. All right, so let's move on to how to come up with the inverse of a function, okay? And then we're going to build from there and graph the function and its inverse. Okay, well, remember how we took a set of ordered pairs. I'll just put up an ordered pair here. If that was one of the points in our relation, to get the inverse, we just switch places with x and y, right? Well, that's exactly what we're going to do here, except that we're going to switch places with the x, y variables. Okay? So instead of f of x, I could just as easily write this y equals, just to give you a y to look at. Okay, haven't really changed anything. F of x and y, synonymous. So if I want to come up with the inverse of a function, I switch places with x and y. Well, it's a two-step process. Switch places with x and y just like you did with ordered pairs. And now you're going to solve for y. So I'm going to write those two steps. Switch x and y, that's your first move. And then solve for y. Okay, so if I solve for y, I'm going to have to multiply by negative 1/3 on each side of this equation. And once I get down to solve for y form, I want you to do this same thing. Instead of saying y equals, since this is going to represent my inverse, I want you to use that notation. When you get down to that last step where it is solve for y, show me the inverse using the inverse notation. Okay, so it says find the inverse of each function. There it is. Hello? He just stepped out. Okay, so now let's do the second sentence where it says graph the function and its inverse. So that's a pretty easy function to graph. It's linear. Y equals negative 3x. So it has a y-intercept of 0. If we think y equals mx plus b, b is 0. And the slope is negative 3. So from this y-intercept, I'm going to go up 3, left 1, or you could do down 3, right 1. And I'm not going to get the rulers out, but do your best to draw a straight line there. I'm going to change to my line draw tool so I can do straight lines. Change the color. And all right, so we're in business. So here is the function. It's given as f of x equals negative 3x, also known as y equals negative 3x. Okay, well, again, remember, how do we come up with the points? If we know a relation, set of ordered pairs, how do we come up with the points for the inverse? Okay, you switch places with the xy coordinates. So I'm going to do the inverse in red. So you don't necessarily have to graph this guy. I mean, you could, but to me it's easier just to take these ordered pairs. Obviously, if I switch places with the two zeros, I get the same point. But here, this point is negative 1, 3. So for the inverse, I'm going to plot 3, negative 1. Just switch them, just like we did in the previous exercise. Okay? Maybe I'll just give you something to look at. This is negative 1, 3 on the original. So that means the inverse will contain 3, negative 1. All right, and then let's do this other point. This point down here is 1, negative 3. So for the inverse, which we're doing in red, we just take those 2 points, those coordinates, and switch places and do negative 3, 1. So coming up with the graph of an inverse is simple. If you know points on the original, just take some of those points and switch places with the xy coordinates, and you've got the graph of the inverse. Now let me just go ahead and complete this. Okay, so there's something really interesting and very important for you to know going forward about a function's graph and its related inverse graph. There's something true that should be true about those two graphs. Do you remember our parent function, y equals x? Remember that guy? What's it look like? It's linear, y equals x. Okay, so what's the y-intercept for y equals x? Yeah, some of you are making it, which is good. It goes through the origin. So if I ask you to make y equals x, I'll do a dotted line. Y equals x would do this. Remember that? So here's what is always true about a function, which is our blue line, and its related inverse, which is our red line. They should always reflect over y equals x. And when I say reflect, again, here's that word again, you could think of the word flip. If I took the blue line and flipped it over, if you can picture it, pick it up and flip it over the green, I would have the red. Okay, so that y equals x line always serves as a reflection line for an original function and its inverse. And you're going to see that come up over and over again. In fact, when you do these graphs, every time you graph a function and its inverse, I want you to include y equals x. Okay, so just go ahead and, the book's not going to tell you that. You go ahead and just draw that so you can actually see how a function and the inverse reflect over that line. Okay, do you have any questions so far? We're going to do some more of these. All right, let's try this one. The directions are the same. We're supposed to find the inverse function. So to do that, I switch places with x and y variables. I turn this into x equals y plus 4 over 3. So that's step 1. And now step 2 is to solve for y. So to solve for y, I'm going to have to multiply by 3. And then I've got one more step, and that's subtract 4. And now that I'm in solve for y form, I'm going to use the notation. And since this is an h function, this is going to be h, the inverse of h. All right, so our instructions are to graph the original function, and if it makes it easier for you graphing-wise, you could think of this as 1/3 x plus 4/3. So the y-intercept is 1 1/3. And the slope is 1/3. Up 1, right 3. Or if you want, you could go down 1, left 3. And do your best to draw a straight line through those points. All right, so the red will represent the original h function. And now let's do the inverse. Now these linear inverse functions are easy enough just to start at y-intercept 4, count the slope of 3. But you can also take points off of the red and just switch the coordinates and plot those. In this case, I think it's probably easier, since we're dealing with fractions, probably easier just to go ahead and graph this. But I want you to know it works either way. So this has a y-intercept -4. And a positive 3 slope, up 3, right 1, down 3, left 1. And let's connect those dots. And they intersect right on top of that special line, that parent function, y equals x. So I want you to go ahead and include that. That should always be true about a original function and its inverse. They should always reflect over y equals x. All right, any questions so far? Pretty easy so far? Okay, let's do a quadratic. So for quadratic, we're going to do the same thing. We're going to switch places to get the function. We're going to switch places with x and y. So I'm going to turn this into x equals y minus 2 quantity squared plus 4. And then go through the process of the correct steps to solve for y. So to solve for y, if you think reverse PEMDAS, the first thing I would do is subtract. I'm going PEMDAS in reverse. So I'm going to subtract 4. To undo raising this quantity to the second power. By the way, you are going to really get yourself in a mess if you square this. Do not turn this into y squared minus 4y plus 4. That is going to really complicate things. Leave it like this so you can do the square root property. We're just going to do the square root of both sides to get rid of that exponent too. So if I do the square root of both sides, don't forget plus minus. I get that. And now I just have one more step. I need to add 2. And just for sake of readability, so that we don't confuse maybe looking like a number being under a radical when it's really not, I think it's better to put this positive 2 in front. And now that I'm solved for y, I'm going to use the notation of inverse of f. So this represents the inverse. Okay, now let's graph the original. So since it's in red, we'll let the graph of that be in red. This is nice because it's in vertex form, so we can see the vertex of this parabola. What is it? 2, 4. Okay, so I'm going to start at 2, 4, vertex. And we need some points, so maybe let's input 1. That's pretty easy math. If I let x be 1, 1 minus 2 is negative 1, negative 1 squared is positive 1, and plus 4 will be 5. So negative 1, 5, and we have symmetry going through the vertex, so that means I've got another point right here. And really 3 points, I'm going to save you a little bit of time. 3 points will be sufficient for your parabolas. So let's connect the dots. Now let's come up with the graph of the inverse. Well, you probably don't want to graph this guy because we really haven't talked yet about graphing the square root function. So again, just think about these ordered pairs, these 3 ordered pairs. Take those ordered pairs and switch the xy coordinates. So this vertex is 2, 4. That means the inverse would be 4, 2. Just literally switch the coordinates. This point right here on the right is 3, 5. So the inverse should have 5, 3. This point is 1, 5. So the inverse should have 5, 1. And the blue is going to represent the graph of the inverse. And just to drill it, I want you to go ahead and include y equals x. And notice that it's true that the red, if you pick up the red and flip it over the green line, you would get the blue. They should always reflect over y equals x. Okay, what do you think? Not bad so far? Pretty easy? This is pretty important stuff. When you get to these problems, this is probably where we're going to spend the bulk of our time. This is where these instructions complicate things just a little bit. First of all, nothing new. Find the inverse of each function. So let's just go ahead and get that out of the way. So here's the function, and we're going to find its inverse. So we switch places with x and y, and then we solve for y. So the first thing to solve for y is I'm gonna say multiply by a third. Could have also said divide by 3. And now the square root property, we're going to do the square root of both sides. Now I'm going to save you some more time. I'm going to say it's okay to leave. You don't have to rationalize. You can leave that as the square root of 1/3 x. So don't take the extra time to rationalize. That's not really the point of this lesson. And now that I'm in solve for y form, I'm going to show the inverse. Okay, so let's graph y equals 3x squared. It's going to be a parabola, and the y-axis is going to be our symmetry line. I know that because there's no linear term, and the y-intercept is 0. So if I input 0, I get output 0. All right, and what I'm going to do in this case, just to kind of illustrate what's about to happen, I'm going to do the 2 sides of my parabola in a different color, and then I'll explain why in just a minute. So let's work on the right side. What if I input 1? 1, 3? Okay. And let's just go ahead and do one more. I know it just takes a total of 3, but I think one more would be good. What about 2? Input 2. 12? And I'm just going to call this 12. All All right, so I'll go ahead and draw this half of the parabola. And we'll do that in blue. And now I'm going to mirror it across the y-axis in red. So that's a point. And then here's another point that matches that. Okay. All right, so far we've found the inverse. We did that. We graphed the function. Now we're going to graph the inverse. Okay? And the reason why I'm doing the two colors is to kind of illustrate what's this talking about. Well, let's think for a second. If I just take this parabola, we can probably use this one as a good example. When I took the red and I came up with the inverse, we got the blue. Is the blue a function? Does it pass the vertical line test? It does not. And you're going to find that for parabolas, that's always true. The inverse of a parabola, whether it opens up or opens down, which would mean that it opens as a backwards C, the inverse is never going to be a function because it's never going to pass the vertical line test. All right, so what we're going to do is we're going to basically break this up into two parts by restricting the domain so that it will be a function. Two separate parts instead of just one whole. We're going to break it up into two parts. All right, so let's just do the red part coming up with the inverse. All right, so we're going to take each of the red dots and switch the coordinates. Well, obviously, that doesn't change anything here. But this is the point -1, 3. So I'm going to plot what for the inverse? 3, -1. Okay? And this is the point -2, 12. So what will I do for the inverse? Yeah, so I'm just going to call this 12, -2. Okay, well, this inverse really represents two different functions. As you can see, one of them is positive and one of them is negative. Well, the red one, it's kind of easy to remember. It dips below the x-axis. It's the negative one. Okay, so let's think about the domain for the original function that would include just the red piece. How would I state the domain for the original function? That's what this says. How could I state the domain for just the red side? Anybody want to take a stab at it? What would the domain be for just this part of the parabola? Well, it looks like it's coming from -infinity and it's stopping where? 0, okay? So I don't have a lot of room. I'm going to try to squeeze all this in. So for the red piece, to restrict the domain of the original function, we would say domain would be -infinity to 0. And that would attach itself to the negative one of these. Negative square root of 1 over 3x. Okay, it's negative because it's the piece, when I reflect it, it's the one that goes below the x-axis. Okay, well now let's do the blue piece and do the inverse. Well, obviously 0, 0 doesn't change anything, but for the blue, this is the point 1, 3, so for the inverse, I'm going to do 3, 1. This is the point 2, 12, so for the inverse, I'm going to do 12, 2. Okay, so now this blue one is the positive form of this. It's above the x-axis. So if you just look at the original, what would the domain be for just the blue side of this parabola of the original function? It starts where? 0, and it goes where? Positive infinity, okay? So it's really like two separate answers. 0, positive infinity will be our domain restriction, and that will attach to the positive form of this. And now we're done. So just wanted to help you out with this domain restriction that is only really going to apply for quadratics. Does that make sense, what we did? Any questions? We're going to do another one. We may just do one of the next two to save some time. Any questions at all? Okay. Let's just go ahead and do this one. And I'm going to give you a big, helpful suggestion. All right? This is standard form. The best way to deal with these when you're changing them or you're trying to find the inverse is to change them into vertex form. That's one of the big advantages for understanding vertex form. So let's see if we remember how to do that. Okay, in vertex form, we're actually going to put this quantity squared. In the quantity squared, it's going to be x minus 3. Just look at the number in front of x and divide it by 2. I'm going to square negative 3 and get positive 9. But to get vertex form, you always subtract from the end of standard form. Whatever that number squared is, you subtract it. And now I can put 8 minus 9 together, and I got negative 1. It's so much easier to convert the function, to get its inverse from this form than it is from this one. All right, so let's go ahead, let's find the inverse. So let me get a helper. Mackenzie, what do I do, first of all, to get the inverse function? Switch x and y, good. So I'm going to make this become x equals y minus 3 quantity squared minus 1. And then what's next, Hannah? Okay, so what are you doing now, just in case somebody doesn't know? What's the big picture here? Solve for y, good. And she said add 1, good. All right, and Maddie, what would be the next step to solve for y? Okay, square root of both sides, so don't forget plus minus. Sorry. Back up. X plus 1. And we're almost there. Claire, and last step to solve for y? Add 3, and I'm going to put it in front so there's no thinking that it might be underneath the radical. And now that I'm in solve for y form, I'm going to use my inverse notation. This is the inverse function. All right, questions so far? Okay, now let's graph the original. And again, it's easier, I think, to graph out a vertex form because we can see the vertex. The vertex is 3, negative 1. And we just need to generate some points. So let's input 2. And what do I get for the output if I input 2? Corey, what would that be? Okay, if I input 2, I get output 0, which means if 2, 0 is a point, then 4, 0 is also a point. If I lost you, let me know. This is really just graphing a parabola out of vertex form. Let's just do one more. Let's get the y-intercept. How do I get the y-intercept? How'd you get that? Somebody said it. Oh, you're looking up here? What if we were looking at vertex form only? How could we get the y-intercept? For any function. If you want the y-intercept, just let x be 0. Because isn't that x-coordinate for the y-intercept 0? So what if I let x be 0? I'm going to get y is 8. And since I have symmetry right here, I can match that up at that point. And you can go ahead and draw. That would be the parabola representing the original function. Now let's come up with the points for the inverse. So let me just get some help here. Michael, give me one of the points that would be on the inverse. 0, 2. Okay, he took 2, 0 and flipped it and got 0, 2. So I'll do the inverse in red. All right. Dylan, give me another point on the inverse. Negative 1, 3. All right, which is right there. So he took 3, negative 1 and flipped it. Let's see. Abby, give me another point on the inverse. 0, 4. 4, 0 becomes 0, 4. So you can see how it's kind of starting to take shape. So every time you do the inverse of a parabola that opens up, it should be a parabola that opens right every time. Joseph, give me another point on the inverse. Okay, 8, 0, 2, 4, 6, 8. And one more, Zach Lee. Yeah, Joseph just did that one. He did. Oh, you're talking about up here. I got you. You're talking about reflecting. So what is that point on the original? Can we count that out? 1, 2, 3, 4, 5, 6, 8. So the inverse would be 8, 6. All right, so go ahead and connect the dots for the red. But we're going to have to restrict the domain because if we draw the red, let me do my two colors again. Let me do the original. I'll do on the original, the left half will be red, and then this will be blue. Might help us see it a little bit better. Okay, so if I took the red half and plotted those points, would it be this bottom part or the top part? Can you tell? The bottom, okay? So for the left half, let's come up with the domain for just the left half. Anybody want to take a stab at it? What's the domain of the left half? Negative infinity to 3, right. So I don't have a lot of room here. So negative infinity to 3 would pertain to which of these functions? Would it be the positive form or the negative? It's going to be the negative. So we're going to attach that one to 3 minus, back up, trying to squeeze it in, and so this is for the inverse part, that is 3 minus the square root of x plus 1. Question? The 3 here, it's the x-coordinate of the vertex, and that's always going to be true. Yeah, so we're coming from negative infinity, and the red half stops at 3. All right, so how do I say the other half? Zane, what do you think? You're going to turn it over to R1. Can you help us out with that? The domain restriction for the blue part. 3 infinity, and that would go with the positive. Okay? Do you think you get it? Any questions? Make sense? Okay, good. If you think you get it, for time's sake, I'm going to skip this one. But if you want, I'll work it out separately on video, and you can go back and look at it on your own. I'll just let you send me an email if you want to see it. We're almost done. This is our last example. How do we tell algebraically, we're almost not quite there. How do we tell algebraically if two functions are inverses? Well, if you've ever seen this, I don't know, this means if and only if. Have you ever seen that before? IFF. So two functions are inverses of each other if and only if. When we do the composite, this is one of the reasons why we did yesterday's lesson, we're going to do two different composites. Why do you think the result of each should be x? Think back at what our graph looks like for an original function and its inverse. Do you remember something key about those two graphs? What line do they reflect over? Yeah, so this is just another way of proving, and if we get x as a result in each of these composites, then they truly are inverses of each other. So let me show you how that works. So the first thing, it really doesn't matter how you start. Let's do f of g of x. So we're going to take the g function, all of it, and put it in for x in the f function. So this is a review of last night's homework. 4 times x minus 6 over 4 plus 6. Well, when I multiply these, the 4's would cancel, and I'm left with x minus 6 plus 6. Okay, so the composite f of g of x gave me the desired result, but that doesn't necessarily mean that they're inverses. Now, I need to go the other way and do g of f of x. And if I get the same result, then yes, they are inverses. So I'm going to take the f function, 4x plus 6, and it's going to replace x in this g function. So here's where I substituted for x. So in the numerator, you can see how 6 minus 6 is 0. So I get to 4x divided by 4. So we have proven algebraically that these two are inverses because when I did each of the composites, I got the same result, which is x. Yes? Yeah, that's a great question. There are cases where with one it will be x, but with the other one it's not. So you can't just assume when you do the first composite that it's going to work out for the second. All right, maybe we can, this is our last example of this. So let's do the composite f of g of x first. So take the g function, and we're going to put it in for x. One-fourth x squared minus 5 minus 5.
So we've done this composite, and here's the result. And it's probably pretty obvious that we're not going to get x when we do this. 2 times the square root of 1/4 x squared minus 10. There's no possible way to get just regular x out of this. And since we didn't get x with this composite, there's no need to try the other. So my answer for this example is just going to be no. To be yes, to be inverses, you have to get x when you do both the f of g and the g of f composite. All right, so that takes care of example number 4. And now when you get to these problems 42 to 47, you actually don't have to graph these. But what I want to illustrate here is what do we mean by the horizontal line test to determine whether the inverse of each function is also a function. So just for sake of illustration, I'm going to sketch the graph of f of x equals 5x squared. So it's going to have a vertex at the origin, the point 1, 5, and negative 1, 5. And then if we input 2, we're going to get 20, which is up here, and negative 2, also 20. And so if we were to sketch this, it's going to be this little skinny U shape, parabola. Okay, well here's what the horizontal line test tells us. If we, unlike the vertical line test, let me just go back for a second. The vertical line test is what we use to tell whether or not the graph represents a function. And if I can only touch one point every time I draw a single vertical line, then the graph represents a function. Well, the horizontal line test tells me whether or not the function is one-to-one, and further, it tells me whether or not the inverse of this will be a function. So as you can tell, when I draw a horizontal line, I cross 2 points, and so that just tells me that the inverse will not be a function. So really your answer here is going to be yes or no, but if you have to sketch the graph to get a good picture, then or at least to get a rough sketch, and so you can apply the horizontal line test, then go ahead and do that. I will go ahead and tell you that if you're starting out with a quadratic function, the inverse, we talked about this in class, the inverse, which in this case would be something like this, it'd be a u that opens to the right. Obviously, it's not going to be a function because that graph would not pass the vertical line test. But just wanted to give you an idea. You'll see this horizontal line test in the future. The horizontal line test will tell us whether or not a graph is a function. So if I'm able to pass or touch just one point with a horizontal line, then the answer here would be yes, the inverse would be a function. Okay, so we'll try another one. This is the cubic function. So let's just get some points. If I input 0, I get 4. If I input 1, I get 5. And if I input negative 1, I get negative 3. We'll go a little further. If I input 2, 2 cubed is 8, plus 4 is 12. And if I input negative 2, negative 2 cubed is negative 8, plus 4 is negative 4. So this graph is going to look something like this. Rough sketch. Well, applying the horizontal line test here, every time I draw a horizontal line, I'm only going to touch one point at a time. Okay, so in this particular case, the inverse of this would be a function. I'll just say it like this. The inverse of f would be a function. We don't have to come up with what it actually is. We just have to say yes or no. Would it represent a function? Okay, and so that wraps up the notes for this lesson. Oh, I got one more. Sorry. Let's take a quick look at this one. I started doing some points, just some inputs. So input 0, output 12, and I went ahead and did my units in 2s. So this is 0, 12. If I input 1, 1 plus 1 minus 6 plus 12, so that gives me 8. All right, so 1, 2, 4, 6, 8, that's that point right here. And if I input 2, 2 cubed, which is 8, plus 2 squared, which is 4, 8 plus 4 is 12, minus 6 times 2. So 8 plus 4 is 12, minus 12 is 0, and then we've got this plus 12. So I get 12 again. Okay, so here's an example. You don't have to sketch this entire graph, but obviously at this point I've proven that this graph is not going to pass the horizontal line test because with that one line I'm passing through both of those points. So my answer for this problem would be no, the inverse of g would not be a function. Okay, so that's it. That's my last example. And so hopefully you're ready now to work on these problems. If you have any questions, let me know.